first one is controller pointing plus button clicking, something like this. So the second one is head pointing plus button clicking. It's something like this one. So you rotate your head and click any button. However, there are several disadvantages for these approaches. For example, people with hand disability cannot use controller at all. And controllers are not around, or hands are occupied with other activities, other things. For example, if you are watching the movies in mobile VR, so I assume that the popcorn is the one that you're holding on your hand, right? So the third thing is holding the hand in mid-air can cause fatigue very quickly. So we thought there's a need for hands-free test entry techniques. Then we did literature, and we found 3 commonly used hands-free test entry techniques. One is head-based, the second one is eye tracking, the third one is speech. So for the first two, majority of the techniques relied on dual, which is difficult to determine suitable dwell time. For example, if the dwell time is short, then it can cause a lot of issues in inputting. And if the dwell time is long, the test entry speed will be very slow. And there's another issue for eye tracking. For example, eye tracking device is not cheap, and it requires amount of time for calibrating. And also, this is what we found during the testing. We found that using eye tracking could cause a lot of issues because of the data noise. And the third one is speech. So basically, you say the word, and the system recognizes and give you a list of options. But this speech technique have some issues in privacy. And if the background is very noisy, the speed can be affected. Those we propose our solutions, which is low cost, and there's no privacy problems, and it's hands-free and dual-free. Here we show 2 quick examples. One is 1 letter per region ring-based layout, and the second one is 2 letters per region ring-based layout. So the keyboard has a radius of 5.5 meters, and this is done by a pilot study, and it's placed 8 meters away from the user. So we designed our first study. We wanted to investigate the effect of letter per region and the center size, also the alphabet starting position on test entry performance and workload and simulator sickness. We applied a 2x2x3 within subject study. So for letter per region, we have 1 letter per region and 2 letters per region. And the center size, we have small and large. The combination of letter per region times center size is counterbalanced for each participant. And the alphabet starting position, we have top, left, and right. This is also balanced for each condition. So we have 18 participants join the study. The device we're using is Gear VR with a S6H+ device. So basically, the procedure is participant come and fill in the pre-experiment questionnaire, and then they can practice as much as they want for each layout. So to do the experiment, they have to complete 8 formal sentences, and then after each layout, they have to fill in NASA TLX workload and simulator sickness questionnaire, and then go to the next layout. They can also left any comments if they want. So for the first study, we found there is no significant effect of letter per region and the center size and also the alphabet starting position on NASA TLX workload and also the simulator thickness. For test entry speed, we found out there's a significant effect of letter per region on the speed. So 1 letter per region is significantly faster than 2 letter per region layouts. But however, it also caused a significant higher total error rate. But there's no significant effect of the letter per region on uncorrected error rate. We found there is a close to significant effect of center size on the total error rate. For user preferences, we found that user preferred alphabet starting precision start at the top. So all in all, we decided to use 1 letter per region and large center size, and alphabet starting precision start at the top for our foundation layout. But this layout facing one major issue, that is very high total error rate. So in order to lower the error rate, we look at the data and we found out that the reason why the total error rate is high is due to the selection of, for example, if I want to select A and I hit the B, so we narrow down the trigger area of the candidate region. And to further reduce the error rate, we added a spell correction algorithm. This is also open sourced. You can try it. So we set maximal search distance as 2. So this can provide us more accurate word suggestions. We then invented dynamic candidate region for our layout, which is something like this. We will show examples soon in the next slide. So in study 2, we want to test how good our RingText is comparing the 4 other hands-free techniques. So the first one is dual circular. So the dual time is 400 milliseconds for first letter input and another 400 for second letter input. The second one is our dual free circular, which is RingText. So you simply go and hit it. So the third one is dual QWIT. They have the same dual time as the dual circular. So the first one is swap circular. So finally, the last one is swap QWIT. So this is based on the implementation from the paper called iSwap. The study is one-way within subject design with 15 participants. They have to complete 8 sentences for each layout. And the conditions, of course, is counterbalanced. So we found that our RingText outperformed 4 other hands-free techniques in this condition. And however, we cannot, the RingText does not outperform other techniques in terms of total and uncorrected error rates. So in the third study, we wanted to see how good RingText can be for longer term usage. The study is a mixed design with 2 factors. The between subject factors is group. We have novice user and potential expert user. The potential expert user is from the second study. So the within subject factor is session. We have 8 sessions in total, 2 sessions per day, and for 4 days. We get 10 participants join the study. So there is a significant effect of session on the test entry speed for both groups, actually. And there's no significant effect of session on total error rate and uncorrected error rates. We also found out that our usage rate of candidate region is very high. So the dynamic candidate region is well used. Here we show some eye tracking like case-based test entry. So like IK, IS, and iWrite. Our ring test outperform all of them. They also have this like same amount of training time, roughly. So our ring test is also comparable to the speech, which is range from 6 to 13 normally. We're also interested in whether like RingText can be applied to AR or MR devices. So we we invited participants from the study 3 to join our test, and they achieved roughly the same performance as the end of the A session. So we can say that the ring test can be applied to AR and MR HMDs. That's it. Any questions?
I have a bunch of questions, but if anybody else wants to ask them, just go to a microphone. So we have 2 minutes for questions. So if I understand you correctly, the ring arrangement was faster than the QWERTY keyboard arrangement. Is that right?
Yeah.
So are there other arrangements that you could imagine that might have even faster than ring?
It's actually, sorry. It's actually only certain circumstances, because we only test one dual time. Right.
It's only certain circumstance?
Yeah, for QWERTY.
Maybe I didn't
No.
ask. Let me see if
no.
I could ask the question again. You found that the circle arrangement worked better than the keyboard arrangement.
Yeah.
But there might be another arrangement that works even better, maybe a rectangle or tetrahedron or who knows, something that is the size of QWERTY with big spaces for E and small spaces for W. Are there other arrangements you could think of that might be better?
We actually tested the cube one, but it's quite slow.
Oh.
Yeah. And,
Okay.
and the thing is, like, the ring test, is only, like, it shows it outperformed in the second study.
Speaker
but
may
it's
want to set up while you're answering.
Okay.
Keep talking.